So then, yeah, it's my pleasure to introduce the speaker today, Yu Kui from Electrical and Electric Engineering at Melbourne. So Yu completed a Bachelor of Science at Shanghai Jiao Tong University. She then did a Master of Science at the Technical University of Berlin, and after that, a PhD at EPFL Lausanne, which she finished in 2016, if I remember correctly. And then since then, she has had a Swiss Science Foundation postdoctoral fellowship. She also did a postdoc at UC Berkeley. And then after all that, she moved to Melbourne to take up her current position in EEE. She's also a current DECRA fellow. So she got a DECRA in 2022. And apart from that, she's just, her research expertise is in optimization algorithms, optimization-based control, model predictive control, as we hear about today. But then also the other thing she lists on her webpage, which is very interesting, is underwater robotics. So I don't know if we hear about some of that today. Anyway, so it's a pleasure to introduce her, and yeah, the floor is yours.
Yeah, thank you very much for the introduction, Matthew. Yes, so my group works on optimization-based control optimization algorithms, and also with like a strong emphasis on robotic applications. So we do have underwater robots and like surface robots. If you're interested in, so that you know we can do real experiments, and also some like SLAM estimation stuff. Okay, so let's get started. So today I'm going to talk about our work on inexact optimization algorithms for distributed model predictive control with limited communication and the privacy requirement. So first I need to apologize that so the content I'm going to present today is a bit different from the abstract, because Kate mentioned that a few people might be interested in privacy related stuff. So I just added this new piece, and so which is not really included in the abstract. But otherwise, the high-level framework is like similar. Okay, so as I said, we work on many robotic applications. So here I've listed 4 applications, so which we are particularly interested in. So firstly, we are working on underwater robots. So we're doing like control, estimation, navigation, like localization, all these tasks. So compared to like in-air applications like flying robots or ground robots, so the one key challenge for underwater robots is like limited communication. So because for underwater scenarios, we can only use acoustic communication, and which can be slow and unreliable. So it means that underwater robots suffer from limited communication. So this is like the first challenge we consider. And so if we move to the second one, so this is like very commonly used application like autonomous vehicle. So the key challenge from control perspective, control engineering's perspective, is that this application has fast dynamics. So it means that we need to make decision within very short time manner, like microseconds, right? And also the problem, the environment is very complex. So means that we are going to have lots of objectives, lots of constraints. So to summary, we need to solve complex optimization problems within maybe like microseconds. So that's the key challenge. So again, it's like a limited online computational time, right? But still need to solve complex problems. And then also, for example, this is like a special case for autonomous vehicle application, like platooning control. So like this heavy-duty vehicles are trying to save energy, trying to be safer if they stay in a platoon. And this passenger vehicle maybe wants to leave or join the highway, and which requires to firstly join the platoon and then leave the platoon. So we call it like a network changes, so like plug and play type of tasks. So the last one is the power network. So this is like collaboration with my colleagues from Power Group. So like in Australia, so like the power networks these days have also like solar panels or wind farms, and also like individual homes and commercial buildings. So they are like power generator or power consumer, right? For example, if you want to apply optimal control techniques to this application to achieve some control tasks, right, to some control specifications. So these subsystems, so the agents need to communicate. So you need to share information, like how much information, how much energy I'm going to generate today, and what is the plan for the power consumption for my home, for example. And this exchanged information might contain local privacy. So for example, my own schedule. I don't want to share my schedule with like great company, for example, right? And then how can we protect local privacy, right? What is the strategy? Okay, so today I'm going to focus on these two topics, but the other two are also very relevant to the tools I'm going to introduce today. So if you're interested in, so we can discuss them later. And so this is the outline for today's presentation. So I'm going to first introduce the tools. Distributed model predictive control. That is like a sub-branch of optimal control. And the second tool is called inexact alternating minimization algorithm. So it's like a dual computation-based first-order method, but which allows noise errors. Two challenges we aim to solve. So the first challenge is limited communication data rate. The second challenge is privacy violence. Okay, so let's take a closer look at the first tool, distributed model predictive control. So let's again use this multi-agent submarine system. So this minimization problem, sorry, I don't have my pointer today. So this minimization problem is the distributed MPC controller. So at each time step t, we need to solve this optimization problem to find the control input. Assuming that here we have like m subsystems, so for example here we have like 6 onboard robots, so 6 submarines, and each subsystem has its own objective. So the objective can be local tracking errors, can be local power consumption. That means that each robot wants to track like a certain path as close as possible, and want to consume energy as less as possible. And each robot has its local constraint, has its dynamical constraints. So dynamical constraints can include, for example, the model dynamics of each robot, and also may contain some couple dynamics. And so the couple dynamics can be caused by like a low-level controller between two neighboring systems. We can design like a low-level PID controller, try to maintain the distance between two robots, right, around like a certain value. So like we have like some virtual conflicts between two robots. And also subject to some local constraints, like input constraints, for example, batteries and motors have like limited power. And also state constraints, for example, collision avoidance constraints. For example, we can do formation control here to make sure that robots won't crash on each other. Okay, so you say model predictive control is like a powerful control technique. It allows different control objectives and constraints, right? It can, when you are designing the controller, you can take all this into consideration, but there's no free lunch. So the cost of using this technique is to successfully solve this optimization problem in a real-time manner. But the good thing is that, so this optimization problem won't change dramatically online. So something will be changed. For example, the state, the position of the robot might be changed online, and the reference might be changed online. So it means that when we are implementing MPC control law, we need to solve like a sequence of optimization problems. And the neighboring optimization problems are quite similar. So commonly we use tricks like warm starting strategy. Okay, yeah. So this is the DMPC problem. And the problem can be formulated as a distributed optimization problem. So again, we have M subsystems, M agents, and each agent has its local objective Fi, and Zi is the local optimization variable subject to local constraint Ci, and the local variable Zi is coupled via this matrix with the global optimization variable. So like simplest case is that V is just a copy of all local, like a vector contains like a copy of all local optimization variables. That's a extremely simple case. And so here, if we want to solve this distributed optimization problem, let's say we run a distributed optimization algorithm, so each agent needs to exchange information with the neighboring systems, right? And here, if we have communication noise, right? If we want to protect local privacy, so then this is the problem we need to solve. Okay, so this is let's move to distributed optimization. So this is the problem we aim to solve. And let's say we apply like certain distributed optimization algorithm to solve it. So usually there are two main steps. Firstly, we need to solve local problem, right? And then we do information exchange. So in order to guarantee, so K is the number of iterations. That's that T at iteration K, we need to conduct these two main steps. In order to guarantee convergence, so usually we assume that we have accurate communication and we can solve the local problem in an exact way. But let's recall the challenges we consider today. Right? We assume that we have limited communication data rate, which means that the communication won't be accurate anymore. We have quantization noise. And if we want to protect local privacy, so here you say the local solution may contain the local private information. So it means that we may want to add noise to local solutions to protect local privacy. So these two challenges cause the problem, right? So the standard assumptions will be violated. And then how should we design the algorithm and what convergence property can be guaranteed? That's the question. So then we move to the second tool, which is called inexact alternating minimization algorithm. And so the key idea is that this method allows errors. So before I show you the inexact variant of the noise, let us quickly go through the original version of the algorithms. It is called alternating minimization algorithm. For short, we call it AMA. So AMA solves optimization problem in this form. So we call it like a splitting problem. So the objective can be split into two parts. So the first part is assumed to be strongly convex, and the second part is assumed to be convex. And the optimization variables in these two separate, cost functions are coupled via this affine equation. So AMA is very simple. So it has 3 steps. So in the first step, we minimize the object. So we minimize the Lagrangian function with respect to x. And here we fix lambda. So we set lambda to be the solution from the previous step. And in the second step, we minimize the augmented Lagrangian function with respect to z. And here we fix lambda and x. And the last step is the standard dual update, this linear update for the dual variable. The tau is the step size. So this is one convergence result of AMA. So let me first race through the theorem. So if f is a positive definite quadratic function and a has zero rank, then the algorithm converges linearly, and we can derive this complexity of a bound. So this is like the simplest case for this algorithm. And this result can be extended to non-quadratic functions. And we can also remove the assumption that A has zero rank. So that's all possible. Anyway, so this is, so the main message is that we can derive such complexity of a bound, and which is particularly interesting for me because later we can use this upper bound as a Lyapunov function when we are doing stability analysis. We treat the optimization algorithm as a dynamical system. And in order to carry out stability analysis, we need like a so-called Lyapunov function, which is kind of like energy function. So this type of bound is very interesting for me. Okay, so the left-hand side of the inequality is sub-optimality after k iterations, and right-hand side is convergence rate multiplied with initial residual. Yeah, okay, let's move on. So this is one result. Let's recall our distributed optimization problem, right? How can we apply AMA to solve this problem? How should we split the problem, right? So that the splitting formulation can be beneficial for our later challenges. So the idea is here. So I use the color blocks to show the relationship between the original optimization problem and the splitting problem. So here we split, so the first objective F contains all the local objectives as well as local constraint. So since we assume that the local objective is strongly convex, and we can consider local constraint as indicator functions, which is convex. So the sum of convex function and the strongly convex function is again strongly convex. So the first objective is strongly convex. And in this case, we set the second objective to be 0. So very simple. And the consensus constraint will appear in the following couplings. So if we apply AMA to this problem, we end up with this algorithm. So again, I use the color to show the relationship. So green is the first step, purple is the second, and the blue is the third one. So here you say the first step becomes like one local minimization problem. We do not need any. To solve this problem, we do not need any additional information from neighboring systems. And second step is interesting. It becomes a consensus step. So please note that this Z tilde is not Z here. So Z tilde is in like expanded vector of Z, which has the same dimension as D. So this iteration looks like we need a central node to carry out this update, but actually we do not. So if we look at like each element of Z tilde vector, so this consensus step requires local communication. So everyone needs to communicate with its neighboring systems. Okay, and then we, so the last step is again to do this dual update. And this step is again a local update. Local update. Okay, so here you say we have two local updates, but for this consensus step, we need to exchange information, right? Local, each subsystem needs to send information to its neighboring system, and then everyone does its local consensus update, and then everyone needs to exchange the local consensus solution with other neighboring systems. And so let's say we probably need, or we probably have to add noise here. What does it mean? So if we go back to AMA, so basically it means that we need to add noise or errors into these two minimization steps. Let's say we have delta K and the theta K. They are just some noise, can be random noise, can be bounded noise, for example. Yeah, but here the noise can be quantization errors, can be like noise to protect local privacy. So this is one convergence result we delivered for this inexact AMA algorithm. So again, so I used like a simple setup. So consider that all functions are quadratic functions. So just to simplify the notations and to simplify my explanations. But again, this result holds for non-quadratic functions. So the theorem says that if f is a positive definite quadratic function, A has full rank, and then the algorithm converges again linearly. So with the same like the same rate gamma. So gamma is a constant between 0 and 1 times the sum of initial residual and a function of errors. So this is the additional term. So compared to the version without noise, so this is the additional term. So this term looks very complicated, very ugly, so I do not want to show them. But we can derive some sufficient conditions on the error sequence for convergence. So like the one simple quick solution is that if the sequences are absolutely summable, then the inexact AMA algorithm converges to the optimal solution. And why this is particularly interesting for us? Because this result will be used later for our quantization design. We want to design a quantizer such that the quantization noise are absolutely summable. So this is the goal. Okay, So before I move to the quantization part, so let's continue with inexact AMA. Here, this is another result for inexact AMA, which will be needed for the privacy part later. So here we drop the noise in the second step. We assume that we only have noise in the first step. And then we have the following convergence guarantee. So if f is positive definite quadratic function and a has full rank, and then the expectation of the sub-optimality is bounded by this term. So constant plus constant times the variance of the noise divided by k. And here we assume delta k follows Laplacian distribution, but this can also be Gaussian distribution. But Laplacian distribution is particularly interesting for privacy analysis.
Can I just ask a question on that? Because I feel like you're about to move on. I don't want to forget it. I was interested on the last slide of how the distribution of the noise determines the capital delta function. So you just give it, and I was wanting an example. So you just gave an example of Laplacian noise. Yeah, what's the connection between any assumptions you make around the distribution of your little delta and your theta? And
so far, so this is like worst case analysis. We do not make any like the stochastic assumptions on the noise. So this is like a worst case analysis. So all like the function is actually like the function of the norm of the noise. Right, so.
And so for Laplacian noise distribution, what is capital delta as an example? Like what kind of functional form does that take?
Sorry, can you see again? So
for
for
capital delta, the function of the noise.
We do not have that term. We do not have that term because this is expectation. So that one is so previous one is the deterministic result.
Yes.
So the optimality is definitely almost sure bounded by this. And second one is for expectation. So in expectation anyway, so it's not strong. Yeah. Okay. Yeah. So one remark is that the sketch of the proof, it's like a very simple proof, just by using the proof of stochastic projected gradient method. Because here we only have one noise, so proof is simple. Okay, and so this is going to be the tool for solving the second challenge. So if we add noise in this way, and hopefully we can protect our local privacy. Okay, let's come back to the outline page. I have introduced the tools distributed model predictive control, inexact alternating minimization algorithm, and then let's move to the challenges. How can we solve these challenges? The first challenge is limited communication data rate, and which means that we can only send limited number of bits for time step. We need to do quantization. So uniform quantization is like the simplest quantization scheme in communication. The idea is very simple. So let's say Q is a uniform quantizer, and the Q has 3 key parameters. So the first parameter is the number of bits and how many bits we're going to transmit, right? And X bar is the center of the interval, and L is the length of the interval. If we know these 3 quantities, we are able to decode and encode messages. And this is one example of uniform quantization. Let's say here we can only transmit 2 bits, right? We transmit 2 digital numbers, 0, 0, 0, 1, 1, 0, and 1, 1. And so this is the center of quantization interval. Sorry, so here it should be X bar. Sorry for the typos. And L is the quantization length of quantization interval. So for example, X is the value we need to transmit, right? And then we first do quantization. So X falls inside this small interval. So we send out 1, 0. So this is like digital number, right? And so the receiver can do dequantization, right? And get X hat. So this is we call X hat the quantized value. And one property of this quantization scheme is that if X falls inside this quantization interval, then the quantization noise is bounded by this function. So the length of the quantization interval divided by 2 to the power of n plus 1. Okay, so like a quick experiment, if we apply this uniform quantizer to a distributed algorithm, for example, consensus algorithm, so the most basic algorithm, right? So assume that here we have 5 nodes, and each node has its local value, local initial state. And the goal is to achieve consensus, so the average of the initial states. We can run this average consensus algorithm to achieve this goal. So W is a double stochastic matrix. If we use uniform quantizer, what would happen? So this is the behavior of the algorithm. So it converges to a neighborhood of the real average consensus. The reason is that the transmission errors, the quantization noise, are not absolutely summable. So the quantization noise is not decreasing. Okay, to improve this property, we propose like a novel quantization scheme. So we call it progressive quantization scheme. So the idea is to let the quantizer to track the iterates. So concretely, what do? We set the mid value of the quantizer to be the previously quantized number, so x hat k minus 1. And we set the quantization interval to be a linearly decreasing function. So kappa is a value between 0 and 1. Okay, so this figure illustrates the idea of this progressive quantization. So the idea is to let the quantizer to track the iterates. And so the interesting property is that if we can guarantee for all iterations xk falls inside the quantization interval, then the quantization noise decreases linearly with the constant kappa. Why this is interesting? Because then the quantization noise becomes absolutely summable, right? Okay, so let's try to combine these two things together. So progressive quantization and the distributed optimization using inexact AMA. As I said, we are going to have 2 communication steps, right? If we add quantizer to these 2 steps, right, you have these 2 quantizers. So they are both progressive quantization. They both use the progressive quantization design. And so this is like the sketch, like development flow for this method. So we first try to find sufficient conditions on the number of bits and the initial quantization interval to guarantee that for every iteration, zk of vk, so the transmitted value, fall inside the quantization interval. So this is like the challenge in the proof. And then we can guarantee the errors are absolutely summable. Then we can guarantee the algorithm converges to optimal solution. Right. So here this is the main theorem. So I do not plan to show the proof. Let's quickly go through the main theorem. So it says that if the decrease rate kappa is a number between gamma and 1, so gamma is the decrease rate, linear rate of the original algorithm, so without quantization. And if the quantization parameters, so initial quantization interval C1 and C2 satisfy some polytopic constraints, so we can find the fast C1 and C2 by solving an LP offline. Then for all iterations, the transmitted values fall inside the quantization interval, and we have this complexity upper bound. So the sub-optimality is upper bounded by a linear function times the initial residual time plus constant delta. And the delta is a constant determined by C1 and C2. And C1 and C2 are determined by N and kappa. Okay, and there, so if we look at the concrete bound, so there are some trade-off, like how should we choose C1 and C2? You can imagine, so if we choose like a small kappa, which may lead to large C1 and C2, right? So although the algorithm convert, like the rate is better, but the constant is huge. So what is the best choice for this quantization setup? Yeah. But all these parameters can be found offline. So before we run this optimization problem, we do not need to know online information. Yeah, so this is like a simple simulation example. Now here we apply distributed MPC to a building control problem. So this is the, I worked here as a PhD student. I use it very much. So the goal here is to do temperature control and to also guarantee that the power consumption is tracking some given reference as close as possible. So here, this is the DMPC problem. So we at every time step T, we need to solve this minimization problem. So here you say we ask the sum of the total power consumption to track some given signal from the grid company. And we also have some local preference. So for example, people in this room want temperature to be 23, but people in this room want temperature to be 20, for example, some local preference. And subject to local constraint, it can be some comfort constraint, temperature constraint, like thermodynamics, dynamic constraints with weather predictions, for example. Okay, so here you say, so K is the index for optimization iterations, and the T is the index for the control loop. And at each time step T, we need to solve an optimization problem, like run maybe K iterations. Okay, so here you say, as T increases, we have different state measurement. We also have different reference. So it means that as T changes, so the optimization problem slightly changes. It's parametric optimization problem. Okay, so let's make like a very naive assumption. At each time step T, we can only transmit 64 bits. So what is the best way to use this 64 bits? We can either run more iterations, but each iteration with fewer bits, or we can run fewer iterations, but each iteration has more bits. Right. So what is the best choice? So the x-axis shows like the number of bits per iteration or the number of iterations per time step. And the y-axis is the normalized average sub-optimality. And for this example, it shows that this is optimal solution. The best way to achieve the best sub-optimality, we want to use the 64 bits in the following way. So we run 8 iterations, and each iteration consumes 8 bits. So then we get the sub-optimality. Okay, now, so since I'm control engineer from like a control research working in control engineering, so I cannot stop myself from presenting something from control. Apologize if it makes confusion. Okay, so now let's try to add the control loop. So this is the optimization algorithm, right? At each time step T, we solve like an optimization algorithm for K iterations. And here we assume that at each time step T, we can only consume like a certain number of bits, for example, 64 bits. It means that we have to quantize the values. We also have to early determine the algorithm. So anyway, we're going to have a suboptimal solution. Okay, so this is like the entire control loop. So we first measure the state and also probably the updated reference. And we update the initial quantization interval. So this is an additional step. So but now you can, it's not very important. But here we use warm starting strategy. We set the initial solution for the current step to be the suboptimal solution from the previous step. Okay, so warm starting strategy. Then, so that's the research question, right? So what is the condition? How many bits we need to guarantee that this loop is stable? Right. One step is missing. So we solve this optimization problem and apply the control input to the system, and then measure the system state again. So then how many bits we need to stabilize such a system? Okay, so this is the stability theorem. It says that, so I hide some assumptions from control. So under mild assumptions on the system and the MPC controller, so if the number of bits n satisfy certain lower bounds, if the number of iterations satisfy again some lower bound. But here, so they are like three constants. So M1 and M2, they are constant determined by the system parameters or the parameters in the controller. But the Mn is a parameter determined by the number of bits. That means that in order to find such a lower bound, we need first to find n, which satisfies like a certain lower bounds. But all these things can be done offline. So without doing like real-time control experiments, we're able to find all these parameters. So they're offline procedure. And then the closed loop system is asymptotically stable and state input to state stable with external noise. So this is like a very strong stability result in control. So the key idea, so I do not want to dive into theory, but I really want to explain the key ideas because the tool might be interesting for you. So the tool, so for doing this proof is called small gain condition. So small gain condition, so the idea is simple, but it is very useful. So for example, let's say if we have one loop, right? So just forget about the middle step. We have the plant, we have the optimizer, we have one loop. So we can analyze these two systems individually if we can find the Lyapunov function for these two individual systems. Good. And then if we couple them together, so this is function composition. And if this composition is smaller than identity function, then we say this loop is asymptotically stable. So this is a sufficient condition, can be conservative, but it's very useful because all these Lyapunov functions can be found by just looking at each individual system. Right? You do not think about these interactions. You just analyze them separately and put them together by using this condition. So that's why this is quite useful in nonlinear control theory. Okay, so the key idea here is to use small gain condition to prove stability, to find the condition on K. And we need to guarantee that small gain condition holds for each loop, for every loop. So this big loop, small loop, small loop, and small loop. If this condition holds for all circles in the network, and then we can conclude that the closed loop system is asymptotically stable. And here you say we have the original system, which is the plant, and the building, and we have optimizer, so as one additional dynamical system, and the quantization interval updating rule as another dynamical system. Okay, so this is the main result of the first part. So let me quickly make a summary for the first part. So in the first part, we considered the following problems: distributed optimization with limited communication data rate. So we look at the tools, including distributed MPC and inexact AMA, and derived for the inexact AMA, we derived sufficient conditions on the error sequences for convergence. So if the errors are absolutely summable, then we are good. And then we, inspired by this result, like we proposed like a so-called progressive quantization design. And the key idea is to let the quantizer to track iterates. And if the quantization interval is said to be a linearly decreasing function, then the quantization noise are absolutely summable, and we have convergence guarantee. And I also quickly explained how can we use this result to do stability analysis, right, for real-time DMPC. And here we, again, by using the complexity upper bound as a Lyapunov function for the optimizer, right, we can derive sufficient conditions on the communication data rate for stability. How much time do I have? How much time do I have?
10 to
minutes?
13 minutes, something like that. Yeah.
The second part is quite short. Oh, do you have any questions on the first part?
Okay, yeah, I have a question. So, are there other conditions for convergence of the inexact algorithm that don't require absolutely summable errors? Because for privacy, if you have summable errors, that's essentially saying like the more iterations you run, the less noise you can add, the less privacy you're going to have. So yeah, but you're saying it is possible.
That's true. For the worst case analysis, it's hard because that's the worst case analysis. So the bound holds in a deterministic way, right? So that's why we move to stochastic setup. And with, you can say with certain probability, right, you have this sub-optimality guarantee, and also with some privacy guarantee. I think that you can also derive other type of sufficient conditions on the error term, but they are also quite strong in terms of if you consider to use them in the privacy setup. Yeah, okay. According to my experience. Okay, so the second part is to add noise to protect privacy. So how can we do it? So before we look at algorithms, let me quickly introduce a privacy concept called differential privacy. So here the goal is to solve a distributed QP while protecting some local parameters. So local parameters can be local quadratic matrix, linear vector, and the local polytopic constraints. So like 4 matrices. And this is the definition of differential privacy. I think some of you might be very familiar with it. So let's say we have 2 different parameters, right, which we want to protect. And they are different, but from like the same given set. And if a randomized algorithm A, so A can be the distributed optimization algorithm, right? It's said to be epsilon I differential private, then the following inequality holds. So what does this following inequality mean? So let's look at the figure. I think that's easier to explain with the figure. So let's say Z is our observation, right? So this is what we observe. Then what is the probability of observing this Z with parameter rho? And what is the probability of observing Z, right, with another parameter rho prime? So the ideal case, so these 2 curves, right, shows the distribution of this probability of this event, right? So the ideal case is that these 2 curves overlap, right? Although you have different parameters, rho and rho prime, you still observe that any Z with the same probability for 2 cases. Right? So this is so we hope these 2 curves can overlap. And if we come back to this definition, right, so it means that we want epsilon I to be close to 0. We want epsilon I to be very small. So we call epsilon I the privacy level, right? The smaller the privacy level is, the better we can protect the privacy. Right? So the distribution overlaps. Okay, let's move on. And let's recall the distributed optimization problem and the algorithm. So as I said, so the local solution contains the information of local constraint and local objective. Right? And we want to protect this information. And the idea is that we try to add noise here to protect our local information. And here we assume that the noise follows like a Laplacian distribution with 0 mean. Oh, very sorry. Yeah, so this is the theoretical result for the privacy part. So this algorithm is epsilon I differential private for node I after k iterations. And the privacy level epsilon I is equal to this term. So it is equal to a constant times the sum of the inverse of the variance of the noise. And if we move to the optimization part, so the result is very similar to the previous case. So the expectation of sub-optimality is bounded by this quantity. So a constant, so here is number of iteration k, and GI is again a constant, you can ignore it. And sigma I is again the variance of the noise. So if we put these 2 bound together, right? So the privacy level and the sub-optimality of a bound. So here you say, as I said, we want the privacy level to be small, right? So here you say, the more iterations we run, the better, so the worse the privacy level is going to be. So the bigger it will be, right? But the more iteration we want, the better suboptimality can be guaranteed. Right? And also if we add like great noise, right? So the privacy level decreases. That means the privacy can be better protected. But if we increase the variance of the noise, then the suboptimality guarantee becomes worse. So this is the trade-off. Right? You can add more noise to protect your privacy, right? But maybe the control performance will be sacrificed because the solution becomes more suboptimal. Okay, so this is like the rough idea of trade-off. And so one idea is to use this trade-off to, for example, design the price for privacy. Okay, so again, let's recall this example. And so this is like the plot for different number of iterations for the trade-off. So the suboptimality and the privacy level, like very simple illustration. And so this concludes my presentation today. So quick summary for the second part. We consider the distributed optimization with local privacy. Again, we use the tool in exact AMA, and the idea is to add noise to local solutions to protect local privacy. And we derive some theoretical results to show the trade-off between suboptimality and privacy level. Yes, so that's all for today. Thank you for listening.